Hello, this is Andy Schweitzer. Quick little introduction into our first video of kinetics. Kinetics literally means movement, and we are looking to track the speed of a chemical reaction. Now, one thing I will just point out to you that there is a definite difference between the speed of a chemical reaction and equilibrium. If we have a reaction, let's say A goes to B, and it goes to equilibrium, let's say, then I often show this little picture, which is the concentration of A, concentration of B, and at some point we form a balance between the two concentrations, and I call that, well, it's called K. This would be a product favored reaction. Now, eventually these concentrations come to some balance, which is concentration of the products or the concentration of the reactants. But if we were to dump into a beaker some amount of K, A, and some amount of B, we get some mixture which wasn't at this balance. At that point we call that ratio Q, called the reaction quotient. That same thing, it's just not at the ending ratio. So this thing is going to give an opportunity to travel towards, or it's going to lose product, in this case lose reactant, gain product, in order to get to the right balance, which is K. Now, this balance, K, has nothing to do with with kinetics. What kinetics is how fast do you get to K, right? So a catalyst, for example, might increase the rate at which you get to K, but it's not actually going to change K, right? Temperature, concentrations, they might affect the rate at which we get to K, but it's not going to change K. Now, as far as kinetics is concerned, okay, we need to have some way generally to track a chemical reaction. I'm just going to start up a new slide here, and let's just say, for example, how do we track a chemical reaction? Okay, well, usually what we track a chemical reaction is by some physical feature. A plus B yields C plus D, and there could be some coefficients here. Let's just say that. Okay. So the way we track something is we don't need to be able to follow everything in this chemical reaction, because everything is locked by these coefficients. For example, if you have, let's say, a teeter, I think that's how you spell it, teeter totter, okay, and it's got a little fulcrum, and you're across it here, and you got a little kid on this side, and you have another little kid on this side. If you want to track the relative positions of your teeter-totter, okay, you don't have to track both sides. You know that based on this height, you can mathematically figure out where this one is, and vice versa. If this one goes up, I can track where this one is. They're locked together. Whenever I lose 2 A's, I also lose 3 B's. Whenever I lose 3 B's, I gain 4 C's. Whenever I gain 4 C's, I gain 5 D's. So in reality, we only need to track one of these items. Now, how would you track stuff? You could track acidity. You could track color with a spectrophotometer. You could possibly track mass, okay, with a scale. For example, on that note, I could just simple example. Sometimes I'll start class off with this particular situation with a candle. Okay, the candle's got a little flame on it. It's burning, and it's burning at a certain rate. I'll set this particular candle on a scale. Too bad I'm not a better artist. All right, and it'll have a certain amount of mass on there, and we'll just track the mass of the candle. Okay. Now, Other things might be gas production. You could easily track that. Gas production. Okay. Any physical feature you can track. So, in that case, regardless of which one I want to track, I can just pick that out and watch it. Okay. And it would be change, your speed would be change, how much stuff changed, okay, per time, okay, and this would literally give you your rate. Your rate would be in something change per something time. Now, pretty common ways in which we could measure this or write it down. Your rate would be in, let's say, moles per second. It could be so something per time. The time obviously can change. You could have it in grams per time. So either way, I think if you were tracking color, which would be percent transmittance, you would then convert percent transmittance to some sort of some other unit, maybe into moles per liter per time. So different things of that nature. Okay, but either way, you'd pick out some physical feature that you'd want to track. Now, it is a possibility that you would have something that has no color on the reactants or the products. They're both aqueous, clear solutions. It might be difficult to track this chemical reaction. Some way, shape, or form, you need to find some way to track this chemical reaction. You might even, if you can't find a way to track A, B, C, or D, you might end up doing a secondary reaction, which you would maybe expose D to E, and E would produce something that you could track. There's all sorts of creative ways that you could do this. This is where an engineer comes in and says, oh, okay, we're going to use a chemistry in this fashion to do something we want to do. Okay. The last little bit I'm going to talk about this reaction is what I call rate within a reaction. This relates to what we were just talking about. A plus B yields C plus D. I'm going to go 1, 2, 3, and 4. Okay? So at any point, if they give you the rate, and I'm assuming on the reactant side that we're consuming these guys, and that we are producing, okay, if they give you any rate of any of these guys, you know, based on the stoichiometric ratio, you'd be able to figure the rate of everything else. Okay, so for example, if they say that D is being produced at a rate of 2 moles per hour. Simple. Okay. Now, if 2 moles per hour, they might say, okay, what rate is the C being produced? Okay. I would simply say, okay, 2 moles per hour, and this is of the D. Factor label or unit analysis, get rid of the D and go to the C, and you know, for every D you also produce 3 C's. 2 times 3 is 6. 6 divided by 4 will be 6/4. Looks like a pretty simple mathematics, which is of course 3/2 or 1.5. Okay. And that would be in moles per hour. Okay. Now this is referring to, in this case, C. If I were to talk about B, I would say, okay, well, same problem. How much is B being consumed? Well, you should note that if you're producing this at 2 moles per hour, then you should be consuming this at a 4:2 ratio at 1 mole per hour. The math would be 2 moles per hour, dot line, this is of D, get rid of D, go to B, use my stoic ratio, 4:2 ratio, the answer is 1 B per hour. Now, sometimes it may have it be negative because you are using it, okay, or you're losing that amount per hour, so it would be negative. I call it rate within the reaction. Other than the general introduction to stoichiometry, this is my first main concept of this topic.